Well, hello there. Good afternoon, everyone. Welcome to the Academy's Morrison Planetarium and to this, our final planetarium show of the day, and this is our tour of the universe. Now, I'd like to find out how many of you have seen our other shows today, either Living Worlds or Expeditionary. Okay, quite a few. All right. This show is a little bit different. Now, this is not a pre-recorded, pre-rendered show. This show is performed entirely live, and it involves a flight through a digital three-dimensional model of the universe using software that is supported by NASA and which you can actually download for free at home. If you like what you see on the dome during this next half hour or so, come and see me at the control booth afterwards, and I'll tell you how you can get the software. Now, since this is a live flight, I'll be piloting us and telling you about some of the things that we encounter along the way. I promise not to fly into any black holes or crash into any planets. However, because there is an amount of motion involved here, if you find yourself feeling a little sensitive to the movement across your whole field of view, because this is a very immersive environment, just close your eyes for a minute or so, and that sensation of discomfort should go away. As with all of our shows, we would like to mention that during the presentation, we'd appreciate it very much if you could please refrain from eating, drinking, snacking, or any kind of photography or recording. This is also a great time to silence your personal electronics and to turn off or tuck away any light-emitting devices like cell phones, tablets, flashlights, cameras, etc. And at the end of the show, which will be about 5 o'clock, about closing time for the museum, at the end of the show, we ask that everybody please exit out through the doors at the top of either stairway. Now, if getting all the way up these stairs is going to be a problem for any of you, especially from the lower rows, then just stay in your seat at the end, and our staff will assist you out the lower exits if that's more convenient. But everybody else, please use these doors here at the top. So, with that, we invite you to settle back in your seats and make yourselves comfortable. Are you ready for a trip into outer space? Huh? What? Oh, okay. All right. So we're going to start by first going someplace where we usually, or where some people usually start their journeys into outer space. And to do that, I have to turn down the lights and bring up this image right here. You know where we are? We are 10 kilometers above Cape Canaveral. And this is where a lot of US missions into outer space begin. And you can see a number of famous features here. Pad 39A, right here, Pad 39B. This is where NASA's new moon rocket's going to launch from. Vertical assembly building. And this is the landing strip that the space shuttle used. It's still there. Now, this is 10 kilometers above the ground. We're going to go up a little bit higher than that, about 10 times this distance as we travel into outer space. One famous astronomer once said, outer space is not that remote at all. It's only an hour's drive if cars could go straight up. And that means that the official boundary of outer space, or at least the officially recognized boundary of outer space, is about 100 kilometers, which is right here. Roughly 62 miles, or about the distance from San Francisco to San Jose, or San Francisco to Santa Rosa. And this is where the air is so thin that control surfaces like wings, flaps, rudders don't work. You have to use rockets to maneuver around at this altitude. Now, it varies depending on where you are with the Earth and how much the atmosphere expands or contracts, but generally they use this distance, 100 kilometers, as that boundary. But we're going to go higher than this. We're going to go four times this height, 400 kilometers, or about 250 miles. And that is the orbital altitude of the International Space Station, so about here. So now we can see more of Florida. And as we cross over, you can see more of the US. This is the kind of view that the astronauts on the space station have as they travel around the world once every 90 minutes at a speed of 17,000 miles an hour. Beautiful view, isn't it? That's the farthest that humans travel from Earth right now. But about 50 years ago, they used to go farther. 50 years ago, during the Apollo program, astronauts went even farther away from Earth, about about 1,000 times the altitude of the International Space Station. So they would go way out, about 250,000 miles out, roughly 250,000 miles. And we're showing you some orbits of the other planets. I should probably turn those off. That's a little distracting right now, so let's get rid of those. And let's have a look at where the moon is. I see the moon right now. It's not too far away. It's a really faint object over here. We're going to zero in on the moon and center ourselves on it so we can have a good quick look at our satellite right there. Now let's travel to the moon. It took the Apollo astronauts 3 days to get there. We can do better than that. At the speed of light, it takes about 1.5 seconds. But here we are at the moon, our own satellite. And this is Earth's nearest neighbor in space. It's a huge ball of rock, about 2,000 miles across. And actually, I'm going to light things up a little bit so that we can actually see the surface of the moon. Let's see, I have to turn off the shadow right there. So now this is the familiar face of the moon as we see it. And you might recognize a few things here. If you're familiar with looking at the moon, you can see some of these dark areas called maria, which is a Latin word. It means seas. Because early astronomers thought that these dark patches were seas. They thought they were bodies of water. But they're not really bodies of water at all. They're large flat plains of dried lava that bubbled up about 1 billion or so years ago, spread out, covered over the rougher terrain, and then cooled and hardened into these flat rocky plains. And then you've got the higher areas here where a lot of craters can be seen. Those are called the highlands. See some very, very large craters here on the highlands. That's the surface of our satellite, the moon. And there are plans to return to the moon in the next 5 to 10 years. And that's where that big moon rocket is going to launch from that I pointed out at Cape Canaveral, called the Space Launch System, part of the Artemis program, the follow-up to the Apollo program of 50 years ago. And one of the things that the Artemis program is going to do is they are going to try to land humans at the South Pole of the moon. Why the South Pole? Well, not too long ago, a number of years ago, a spacecraft found evidence of ice in the deep craters at the South Pole of the moon. And if there really is ice there, then that would be a source of water that could be used in future manufacturing efforts on the moon. If there's water there, they can break it down into hydrogen and oxygen, and those elements can be very, very useful. Oxygen to breathe, hydrogen to make rocket fuel with. So that's one thing that scientists are very excited about being able to do as we return to the moon. But now, let's travel even farther out than that. Now, I said the moon is our nearest neighbor in space. We do have other neighbors, and earlier I gave you a glimpse of some of those other objects. Let's turn on the trails of the other planets in our solar system so we can have a good look at where we are in our immediate neighborhood in space. There's the sun over there, over on the left-hand side, our own star, the nearest star to us, 93 million miles away. But at the speed of light, it takes about 8.5 minutes for the sun's light to get to us here on Earth. And that's a very handy measure of distance that astronomers like to use, because when we talk about things out in space, we start talking about things that are so far away and the numbers being so big that using miles is ridiculous. It's kind of like trying to measure the length of Golden Gate Park in millimeters. So they use the speed of light as a really good measuring stick or yardstick. So Earth and the moon are about 1 1/3 light seconds across. It takes 1 1/3 seconds for light to travel from Earth to the moon. From Earth to the sun takes about 8.5 minutes. So the sun is 8.5 light minutes away. And what that means is that if anything were to happen on the moon, we wouldn't know it for about 1 1/3 seconds. If anything happened on the sun, we wouldn't know it for 8 minutes, because the light from those objects takes that long to get to us here on Earth. So that's a good way to estimate how far away things are, how long light would take to get to us. Well, of course, the Earth is the third planet from the sun. First is Mercury, then Venus, then Earth. then following Earth is Mars, the fourth planet, the red planet, one which is very interesting to many scientists. And then after Mars, there's a big gap, a wide gap between Mars and the next planet out. That gap is filled with a lot of chunks of rock and debris and rubble left over from the formation of the solar system. Those are the asteroids. And then after the asteroid belt comes the realm of the giant planets, starting off with Jupiter, and then Saturn, and then Uranus and Neptune. And those are the 8 planets orbiting the sun that we recognize today. Now, there are other things orbiting the sun. For example, if we were to travel just a little bit farther out, we would see that the orbit just beyond Neptune is also crowded with all kinds of other things. It's sort of like the asteroid belt, but a lot messier. This is called the Kuiper belt, or the zone of trans-Neptunian objects, as they're called. And these are lots of comets and what are called dwarf planets, and that's what Pluto has been reclassified to. It's no longer considered a major planet, but a dwarf planet. And there are 3 other dwarf planets out in that area. But in this region, we've got lots of short period comets that return to the inner solar system about once every, within 200 years or so. Even farther out than this, there's another zone of planets with long periods. So we're not going to talk about those. Those are way out there. But that's the Kuiper belt, which to some people marks the edge of the solar system, but it really depends on how you want to define the edge of the solar system. One other way that we can talk about the size of the solar system, though, is by looking at the spacecraft that we have sent out. We talked about how far humans go now to the International Space Station. We talked about how far humans traveled from Earth 50 years ago to the moon. And now let's have a look at the farthest that we have sent any spacecraft out from Earth. And those are indicated by these lines here, which you see radiating out from the Earth. These are the 5 spacecraft that are exiting the solar system right now. The one heading off all by itself is Pioneer 10, which was launched back in 1973. And in the other direction, one of these orbits, this one right here, is Pioneer 11. And then you have Voyagers 1 and Voyager 2, which went out to the outer planets and gave us wonderful pictures of Jupiter, Saturn, Uranus, and Neptune. And the shortest path is the New Horizons spacecraft, which passed by Pluto not too long ago and is exploring other bodies in the Kuiper belt. But those are the spacecraft that are now leaving the solar system. And the farthest one is only about 14 billion miles away, which in the scheme of things is not really that far. It's not even as far as light can travel in one day. But it was launched more than 40 years ago. That's how long it took our spacecraft to get out this far. So let's turn off those spacecraft and travel farther out, away from our star, the sun, and now into interstellar space, where we enter the realm of the stars. We're passing various stars as we travel farther and farther out into the universe. And as we do, there's one more thing that I want to point out to you, which is the most distant artifact of human existence. It's not a spacecraft. The farthest evidence of human existence in the universe is something that is indicated by our radio signals. This big round bubble here is what's called the radiosphere. It is our radio footprint. It is how far out into space our radio signals have traveled from Earth in the past 90 or so years that we've been broadcasting. So that's how far out into space any evidence of humanity has traveled. So if there are any civilizations within that bubble, within that 90 light year radius bubble, they might have heard our radio signals. But if there's anybody outside, they don't know about us yet. They haven't received our radio signals. Interesting thing to think about. But let's leave the radiosphere farther behind now and travel farther out into space. We haven't even left the galaxy yet. We're still traveling through the stars of the Milky Way. And as we travel farther and farther and farther out, eventually we'll see where we are in the Milky Way galaxy. About 100 years ago, astronomers thought the Milky Way was the only galaxy in the entire universe. Now we know better. Now we know that the Milky Way is just one of lots and lots of galaxies. And here's where we are. I left the radiosphere on. That's where we are in the Milky Way. Not at the center, but off about 2/3 from the center. That's our location. The Milky Way is a huge flat disk of several hundred billion stars. And you can see it is very flat as we pass through the plane of the galaxy right now. And it is so wide, so large, that it takes a beam of light 100,000 years to cross its diameter. Now remember, I said the moon is 1 1/3 light seconds away. The sun is about 8.5 light minutes away. The nearest star to us, Alpha Centauri, is about 4 1/3 light years away. The Milky Way galaxy is 100,000 light years across. It takes a beam of light that long to cross its diameter. And the Milky Way is not the only galaxy in the universe. Again, I said about 100 years ago, we found out that there are other galaxies in space. That was courtesy of Edwin Hubble, after whom the Hubble Space Telescope is named. The Milky Way is not just one of many galaxies, but the universe is actually expanding. The galaxies that we see are moving away from each other, so the universe is getting bigger and bigger. The Milky Way is just one member of a cluster of galaxies called the Local Group, which contains about 80 or so galaxies. And now that we've left the Milky Way, every spot of light you see on the dome overhead is not a star, but a whole galaxy. And each one of those galaxies can contain several hundred billion stars, like our own Milky Way. Now, I'll point out one other galaxy to you, which is this one right here. I think it is the Andromeda Galaxy, the nearest large spiral galaxy to us. It's pretty much a twin of the Milky Way, but it's about 2.5 million light years away. So far that its light takes 2.5 million years to reach us here on Earth. So if you want to know what's happening on the moon, when you see things happening on the moon, it takes 1 1/3 seconds for that light to get to us. Things happening on the sun take 88 minutes to get to us. In Alpha Centauri, 4 1/3 light years away. That's what those objects looked like, those intervals of time ago. I mean, when we see Alpha Centauri in the sky, we're seeing the way it looked 4 1/3 years ago, because that's how long its light took to get to us. When we look at the Andromeda Galaxy, we're seeing something whose light left it 2.5 million years ago. That's what it looked like 2.5 million years ago. If you want to know what the Andromeda Galaxy looks like now, today, in 2022, you have to be patient. You have to wait for the light leaving it right now to reach our eyes 2.5 million years from now. Mind-boggling, isn't it? Let's travel on. And speaking of galaxy clusters, I talked about how the Milky Way is part of a local group. That's what we call the cluster of galaxies to which we belong. I'll show you a picture of another cluster of galaxies, one that was taken not too long ago by the James Webb Space Telescope. And this was the first image that was released to the public from that telescope, showing this galaxy cluster right here, the white blobs you see right here in this chain. And that galaxy cluster is about 5 billion light years away. Farther out than that are other galaxies whose light has been bent by the mass of this cluster of galaxies and distorted to form these arcs, these reddish-orange arcs that you see. This is a phenomenon called gravitational lensing, and it's something that's well known to astronomers. We've seen it in lots of other images of the universe. But those galaxies, those arcs, are much farther away than the nearby cluster, 5 billion light years distant. So it's amazing what this telescope can do, and we're looking forward to seeing what else it'll do in the next 20 years that astronomers expect it to be in operation. Okay, so as we travel farther out, We're traveling through large clusters of galaxies or superclusters, some containing thousands of galaxies. And the colors you see are not really the colors of the galaxies themselves. They just indicate the particular survey that was used to observe these galaxies. But as we travel farther and farther out, all of these spots of light that you see, everything you observe, is actually the result of real surveys, real scientific studies. This is all based on real data. And our current map of the universe, our current model, looks like this. This is how many galaxies are here? Lots. But does the universe look interesting? Does it look like a big butterfly to you? Or maybe a big bow tie? Is that the real shape of the universe? Well, no, it's not. The reason these gaps are here is because these are just parts of the universe, parts of the sky that we haven't mapped very well yet, because there's something blocking our view. What's blocking our view is our own galaxy, the Milky Way. Remember, the galaxy is very flat. And looking along the plane of the galaxy, we're trying to look through stars and dust and gas, and that blocks the view of lots of galaxies farther beyond. That's why these gaps are here in our model, in our map. Eventually, as our technology gets better, we'll be able to see more and more out there, and we expect our map to even out and become more uniform and see a better, more uniform distribution of galaxies. The farther out we go, the stranger objects we see. At about 10 billion light years away, we see what are called the quasars, or quasi-stellar radio sources. And those are indicated by the orange spots you see way at the ends of those giant fans. Those are very, very bright objects, which for them to be as bright as we observe them, at the distances we observe them, they've got to be tremendously energetic. And astronomers think that quasars are very young galaxies, maybe newborn galaxies, powered by supermassive black holes at their centers. That's why they're so energetic. And beyond that, well, we don't know what's beyond that. But permeating everything, surrounding the entire universe, coming from all directions, is a microwave background radiation, which was predicted back in 1948 and not discovered until the 1960s. But this is the first radiation that we think was able to travel through space. At one time, about 13, almost 14 billion years ago, astronomers say the universe was so dense, so hot, so opaque, light could not travel from one place to another. But about 300,000 years after the universe began to expand, then light began to penetrate that opacity and began to travel from one place to another. And this is the light that we see. This is actually a heat map of the very young universe. And it shows differences in temperature of the universe and the beginnings of differentiation of matter and the formation of stars and galaxies. That's how it began. So that's as far out as we can see. So since that's the case, we've got nowhere else to go but back home. Now, one thing that may occur to you as we look at our three-dimensional model of the universe, it seems like we're at the center of the universe, doesn't it? I know some people who think they are, but that's not really the case. We're not at the center of the universe. That's only the result of the fact that we're the ones who made the map. It's a result of our perception, our perspective. If there was someone else at some other place in the universe making their own map of the universe, everything would seem to be centered on them. So it's just a matter of perspective, or point of view. As you travel farther in, think about this. Everything we see, all these galaxies and superclusters and quasars and all these huge structures, that amounts to only about 4% of the mass that astronomers think there is in the galaxy or in the universe. By measuring the motion of galaxies, they think that there's a lot more mass out there whose gravity is affecting those motions. We just can't see it. So that's the mystery that astronomers call dark matter or dark energy. There's something out there that we can't see, but which is still influencing the movement, the gravitational interactions between things in the universe. Traveling back in toward our location in the galaxy, we're approaching our radiosphere. Let me show you one last thing, which is sort of related to all the stars that we've seen so far, and that is the number of other possible places where life might exist. Now, there's so many stars out there. Some of them do have planets. Since 1994, astronomers have been discovering planets orbiting distant stars, and they've found more than 5,000 so far. These circles that you see are stars that are orbited by at least one planet. These are all confirmed. Are any of those planets like our own? Well, we don't know, and it's going to be a while before we can actually find out, because these are so far away. It's hard to learn much about them. But you've got to have the right kind of planet. It's got to orbit the right kind of star. It's got to be at the right distance from its star, so it's neither too hot nor too cold. It's got to have the right components to provide nutrients for whatever life might arise on it. So there are a lot of things that a planet needs to be able to support life. And we don't know how many other worlds out there in the universe actually have this. So as we travel back in toward our own solar system, back toward our home planet, in all our travels through the universe, it appears, at least for the time being, that there's only one planet that does have everything that you need to support life, and that is our own planet Earth. Our world and the life upon its surface exists in a very delicate balance with its environment, which we could do better taking care of. So that's a good reminder for us that we can take really good care of our planet, its environment, and the conditions that allow life to exist. And in all our travels, we find there is no place like home, is there? And with that, welcome back home. Back home to planet Earth, back home to San Francisco, back to the California Academy of Sciences, and we thank you all very much for joining us on our tour of the universe.